Yeah, so hi everyone, let's start. So today we're happy to have Giovanni, who's a last semester master student, and he will talk about approximation of functions with neural networks. So please welcome him.
Hello everyone. Welcome to today's talk. Today I'm going to try to talk about like optimal approximation of function with deep neural networks. So in the past years, like everywhere, like computer science, like neural networks and like objects from like deep learning have been used to achieve like state-of-the-art results, and nowadays are the main technique used to like achieve those results. But today we want to like understand like and characterize the fundamental limits of approximation of neural networks. So what does a neural network do? A neural network tries to implement efficiently a function by learning it on couples of input and output data. I'm not going to go further here because I'm not even an expert in this, so like just put it like that. What are we going to try to do today is to characterize the fundamental limit of approximation. What those limits tell us are the theoretical capabilities of those neural networks if no constraint on data and learning algorithm is posed. Now, I agree that like this is a very unrealistic assumption because like most of the time you have to deal with data and also with finding the right algorithm to learn those neural networks. But I think this is a very powerful theory that like tell us theoretically so the possibilities of those neural networks, and so I think it's still very interesting. So in order to do that, to characterize the fundamental limits of neural networks, we will introduce this Kolmogorov-Donoho rate-distortion theory that will allow us to compare the complexity of a function class with the complexity of the neural networks that try to approximate it. So, and we will like at the end like show that neural networks are actually optimal for many of the function classes that are at our knowledge and that we actually use to model like the signal in mathematical signal processing. The whole goal would be to try to give like a theoretical explanation of why neural networks work, and then at the end also to give a brief overview of how we can use this framework that I'm going to develop today for explaining also the success of other objects. We'll first introduce this Kolmogorov-Donoho rate-distortion theory. Then I will use this theory, this framework, to compute and to put this framework into work for approximation with dictionaries. And then I will take some ideas from this approach, extend those to neural network approximation, and then at the end show that like neural networks are actually optimal for the approximation of most of the function classes that we know. So let's just first start from like setting the common ground and fixing the definition of a neural network of what I'm gonna refer to as neural network. So we are going to talk about like ReLU neural network. So we fix the depth of the networks. Then we chose the width of every single hidden layer. And we define the ReLU neural networks as just a composition of affine transformation with non-linearities, and iteratively do that for the length of the neural network. I'll just put this. Maybe it looks very, very strange. I just want to do like a very easy example on what do we like. Why that's like that's a definition for a neural network. So let's fix, for example, a very simple, just a very stupid example, just to be sure that we are all on the same page. Let's fix the input dimension to 3, then the second one to 2, I don't know, to 4, and then the last one to 1. So what does that mean? It means that the input layer has 3 nodes, and it's going to be the first layer. Then we will have a second layer that has 2 nodes. Then we will have a third one with 4. And we will have a last one with 1 that is going to represent our output. So our map, our deep neural network will go from R3 to R. And how we are going to compute the output will be take take the input. So we will have x1, x2, and x3 here, a simple vector. We are going to compute those two nodes as weighted, linear weighted combination of x1, x2, x3, where the weight is given by ay1, a12, and a13, and so on for the other one. So we will have that the affine transformation W1, in the definition of before, we will describe how the input is transformed in this second layer. After computing the affine transformation, we will apply the nonlinearity, and then we will reuse this in the second layer, where W2 will transform these two in the same way that we transform the first, from the first to the second. Then we will reapply the nonlinearity, and then we will apply W3, and we will get our output. So maybe everyone is already like very familiar with how deep neural network works, how they can be defined, but like this was just a very simple example to put everyone on the same page. Now, there are also a couple of important properties of certain deep neural network to which we are going to refer a lot during the talk. So let's just define them. Let's define the connectivity as the number of non-zero weights of all the matrices and of the vector that define the affine transformation. Let's define the depth as the value L, so how deep it is, the network you just draw. The width as how high, what is the height, essentially the maximum height of the neural network. And then the weight magnitude as the essentially the absolute value of the biggest entry in the neural network matrices and vectors that define it. Okay, now that we have fixed the definition of a neural network, we can start by introducing the Kolmogorov-Donoho rate-distortion theory that will be the main tool that we will use to characterize those approximation limits. So let's fix a compact function class C, subset of the L2 function. For those of you that are unfamiliar with working with LP spaces or compact function classes, just think of your favorite function class, so just a set of infinite functions, and just think of them to not behave too widely. So they kind of like behave not too widely, so they're like, it's easy to manage them. And now we are defining the set of all the binary encoders of length L and the set of all the binary decoders of set L. So what are those binary encoders of set L? You take are all the rules, essentially, that assign to every function in our function class C a bit string of L elements. So a bit string of 0, 1 of L elements. And the decoder, what does the decoder do? Essentially the opposite. So it takes the bit string and gives you like a function. Of course, since the set of function is can be made of like infinite function, we are going to realize an error most of the time by encoding the function and then decoding them, because we are always have that the image of the decoding after the encoding is going to be finite and the initial one was infinite. So we say that an encoder-decoder pair realize a certain uniform error if essentially the maximum error that you achieve by doing this procedure is bounded by epsilon. So it's at most epsilon. We can say that the error of the procedure of encoding and then decoding it is always epsilon. So the maximum is epsilon. At this point, an interesting question that one can ask itself is, okay, but let's fix the function class that we want to decode and encode the code. Let's fix an error. What is the minimum length of the bit string that we need in order to achieve that error? And especially, how does this minimum length scale to infinity for the epsilon that goes to 0? And this is exactly the concept that the next two definitions are capturing. So the first one is the min-max code length that just describes simply what I said. So it's just the minimum length of a bit string in order to guarantee the existence of an encoder-decoder pair that realizes a certain error. So for that L, we will always have an encoder-decoder pair that realizes uniform error epsilon on our function class. And now we also ask ourselves, okay, but how does this scale to infinity as the epsilon scale, as the error goes to 0? And this is described by the optimal exponent gamma star. that can be seen also as describing the complexity capacity of the complexity of our function class C. Why? Let's just, okay. Why is this gamma star C describing the complexity of our function class? Okay, so we want to have the min-max code length to be a big O. So we are asking this. We are asking that L epsilon C is a big O of epsilon to minus 1 over gamma. Okay, this can be very strange, so maybe it's not immediately intuitive. So this just means that we want to have L epsilon C to be smaller or equal than a constant C over the square root of gamma epsilon, as epsilon that goes to 0. Now, the bigger the gamma is, the slowlier the square root of gamma epsilon is going to 0 for epsilon that go to 0. And in particular, the slowlier is going to be this value to go to infinity. We will have a denominator going to 0 slowly, so like the whole thing is going to go to infinity slowlier. And in particular, the bigger gamma it is, the easiest it is to encode our function class C to a uniform error epsilon. So this means that, like, essentially, long story short, like if this gamma is big, then it's easy to encode our function class because we don't require a lot of bit to encode that with a uniform error epsilon. Now, okay, now we have defined the we have defined this Kolmogorov-Donoho rate-distortion approach to describe the complexity of this function class. And we will try to use this framework to essentially describe optimal representability of function class with dictionaries. Now, maybe not everyone is familiar with optimal approximation in dictionaries, and indeed, I want to first start from introducing the concept of nonlinear approximation. So, consider an Hilbert space with its inner product and the induced norm, and consider an orthonormal base of the Hilbert space. Now, maybe again, for those of you that are familiar by working with Hilbert spaces, just think of the Hilbert spaces as you already think of. If you're not familiar, just think of your favorite Euclidean space, so Rn, with a huge n, just put like the n equal to million or billions, so like a huge Euclidean space, and take the orthonormal base, so the usual orthonormal base made of like an entry equal to 1 and all the other equal to 0. Just think of that. So like an Rn with your favorite like orthonormal base, the simplest one, the canonical one. And now what you want to do is try to take elements in this space, and you want to try to approximate those elements with just m terms, so just with linear combinations of m terms, so with elements of the type G equal sum of linear combination of m elements, where the m is much smaller. So imagine that you have the space equal of dimension 1 million, and you want to find an approximation with 10 elements, so a very small approximation of your elements. And now you are allowing yourself to take the best one. So you can choose freely among all the elements in your base. You fix the best linear approximation that uses at most 10 elements, and you call that your approximator. In most of the cases, this will realize an error, because probably your elements will not lie essentially in the same subspace of dimension 10. So you will realize an error, and you measure this error and you call it gamma m of f. Now, maybe it's already not clear, but if it's not, then it's gonna get like worse, because now we are allowing for much more freedom. So we are not considering approximation with a combination of elements in the orthonormal base, but we allow for more freedom, and we allow for approximation with linear combination in the dictionary. So what is a dictionary? A dictionary is simply a countable set of elements in the L2 space, the thing that we call there with D. And we now ask for the best approximator that is a linear combination of at most m elements in the dictionary. Now we have this. With this, again, we'll realize in most of the cases an error. We measure the error, and we ask ourselves, how does this error go to 0 if we allow for the m to go to infinity? So when we are letting the number of elements that can be used to approximate our original elements, how does the error go to 0? Because it does go to 0, since like we're allowing for more and more elements to be approximated from until a point where the elements are going to be equal to the elements in the dictionary itself, so the dictionary is going to be able to approximate exactly our function. So how does this go to 0? And this is captured by this, again, like by the best m-term approximator rate of f in the dictionary D. Again, this looks like a very hard definition. It's just characterizing how fast the error goes to 0 as a power of m, essentially. But like the way you can think of this exponent is that it's telling you how easy it is to approximate your function class C in the specific dictionary D that you can choose. So it's a measure of how easy it is to approximate your function class in a certain dictionary. Now, a problem that we have at this point is that we are allowing for very free choices of the elements from the dictionary. So, it's like practically, when we will have to approximate those elements with the linear combination of m elements in the dictionary, we will have to choose the best m among infinite one, because the dictionary has infinite elements. So it's going to be essentially impossible, because we will never find the best m in an infinite dictionary. So we are imposing actually another constraint, that is, we are not searching among all, but we are searching from the first to the last one, where the last one is a polynomial of m. If this doesn't tell you nothing, just think you're not searching from the first to the last one, where the last one is infinity, but you at a certain point stop, and then this ending point is just characterized, it grows as a polynomial of the number of elements that you want to characterize. Then you can redo the same thing. You ask yourself how the error go to 0, and you characterize again this gamma star efficient. This is the effective best m-term approximation rate of C in the dictionary D. Again, it's characterizing how hard it is to approximate your function class in a dictionary when you add the constraint of polynomial depth search, is called. So essentially, where you can search just in the first pi m elements. Now you have a measure of measuring how hard it is to characterize your compact set of function with a dictionary. And essentially, at this point, an interesting question is trying to understand if there exists a relation from this complexity and the complexity of the original class that you're trying to approximate in the beginning. No? The thing that I defined before, the optimal exponent gamma star of C. So you can ask yourself, okay, but does there exist like a relation between how hard it is to approximate a function in a dictionary and the complexity of the function itself? And the answer is yes, actually, because there exists. And in particular, this is never going to be bigger than the complexity of the function itself. So how hard it is to you can never do better than the exponent gamma star of C. And in particular, at this point, with this inequality, it becomes natural to define what it is that we mean by an optimal dictionary. In particular, we mean that when we talk of optimal dictionary, we define an optimal dictionary as a dictionary for which this bound is matched with equality. So if we have a dictionary such that this hold, then we say that this dictionary is optimal in representing the function class. And this was the thing that I introduced now of optimal approximation with dictionaries was a very well-studied domain of the mathematics of signal processing. And in particular, people did come up with essentially all the optimal dictionaries for the most important function classes. So we here have essentially all of the function classes that are relevant in mathematical signal processing. So essentially those function classes are properly modeling a lot of signal that you can think of. So images, sounds, whatever you want to think of, like they're properly modeled by those kind of functions. And people did come up with the optimal dictionary. So we know what are the optimal dictionaries, essentially. And also, you can see also that are actually, just in the names, are very different. And they are actually also very different, like in nature. So there are certain kind of signals that are optimally represented by certain kind of dictionaries. And those dictionaries can also be very different in nature. So this was what was there for a long time, and people studied it and come up with the right dictionaries for the right function classes, and they knew a lot of the domain that of this Kolmogorov-Donoho rate-distortion theory. What we are going to try to do now is to approximate the same framework, so the same idea that we just used now, to come up first with a definition of optimal approximation with neural networks, because it's not even that trivial to define what is the concept of optimal approximation, as it wasn't for dictionaries. And then we're going to try to give an idea on why and how people came up with the proof of why neural networks are actually optimally approximators of essentially all the function classes that I just showed you. So let's again redefine those concepts of errors and of how does the error goes to infinity. And this time, when we are trying to approximate our function, not in the dictionaries, but with neural networks. So with the neural network. So let's again take our function class C, again compact, and then we're trying this time to approximate the function class with a neural network that has at most connectivity M. So before we had the constraint that we were trying to approximate with the linear combination of at most M elements. This time we are translating that constraint in constraint on the connectivity of the network. Let's choose the neural network, the neural network that achieve the minimum error. Let's store this error in gamma in this strange notation. And now let's again ask ourselves, how does this go to 0 for the M that goes to infinity? So if you allow for potentially infinite connectivity, how does this error scale to 0? And in particular, we define again this best M-weight approximation rate by neural networks. That is exactly the same idea that we did before, but this time, instead of approximating with linear combination of elements in a dictionary, we approximate with neural networks where the constraint is put on the connectivity. Again, we can also again create a parallelism with the problem that we had before. So before we were searching in dictionaries that are by nature made of infinite functions. Now we are searching in neural networks where we have like a condition on the connectivity, but essentially there's not enough. Like essentially the idea is that there are too many neural networks from which we can search of. So we need to impose some other constraint. Following my talk, this looks like constraints that are coming a bit from nowhere, and actually they are in my talk. But actually there is a reason why are exactly like those. So why the length has to scale at most polylogarithmically in M, and why the weight connectivity is scaling polynomially in M. But I think it was not very useful to explain why they are like this, the constraint. I think the best way to think of them is exactly by doing the parallelism with what we did before. So essentially there are too many neural networks from which we are searching from, so let's restrict them, let's put these constraints, and now let's search in this smaller class of neural networks which one is the best to approximate our original function. And again, let's define the error, and let's define this coefficient that again measures how easy it is to approximate this function class in with neural networks, where we have put the constraint of polylogarithmic depth constraint, and polynomially weight magnitude constraint. So we have, again, like a measure of how hard it is to approximate a function class in neural networks. And again, we can iterate and say, okay, but does there exist, again, a constraint? Does there exist a natural bound for these exponents? So does there exist a natural way of comparing the original complexity of the function class with the complexity of the function class approximated by neural networks? And actually, a bit surprisingly, one can show that the bound is the same of before. Actually, I'm saying that like it's a bit surprising because if you are thinking to what we are doing two things that are very different actually. Before we were approximating with linear combination of elements, of M elements, and now we are doing linear approximation with neural networks that like by nature are very different from just linear combination of elements. Are composition of non-linearities with affine transformation. So like by nature one would say that like they're very different, but actually it holds the same bound. And then again, this leads naturally to what we define as optimality of representability of function classes by neural networks, because we again say that like if for a function class we have that this coefficient is actually equal, so the bound is matched, then we call this like a function class that is optimally representable by neural network. And after all this, we came up with a definition of optimal approximability of function classes with neural network. The next question is, okay, cool, very good. Like we have a way of defining optimal representability of function classes with neural networks, but maybe this is never matched, because maybe this never happened. So how are you saying that? How you say at the beginning that most of the functions that are used in mathematical signal processing are actually optimally represented by neural networks? Well, actually, in order to do that, we need to introduce the concept of dictionary. We can again reuse all the work that was done for dictionary. We can define the concept of dictionaries that are effectively representable by neural network. Essentially, the idea is that for every element in the dictionary, there exists a neural network that behave properly. Behave properly is a very short way of referring to all those conditions. So you see that the connectivity has to scale at most polylogarithmically in the error and stuff like those. But anyway, you can just think of for every element in the dictionary, there exists a neural networks that approximate the elements quite well. Now, you have this, and you have that the dictionaries are optimal with respect to, and then you know the dictionaries that are optimal with respect to the to the function classes. So maybe the idea is that you could actually use those two things together. And actually, this is exactly the way they show that neural networks are optimally representing most of the function classes, because then, since the dictionary is effectively representable by neural network, you can show that this coefficient is always bigger or equal than the coefficient of the function class with respect to the dictionary that has to be effectively representable. This is a condition that then we will have to say something about. But now that we, at the point where we have this inequality, then essentially the work is done, because we can reuse all the work that was already done for optimal approximation of function classes with dictionaries. Because if we have that inequality holds, then for all the optimal dictionaries that I enumerated before, then it also holds that the same function class is also optimally represented by neural networks. And in particular, this means that essentially, if all those dictionaries are effectively representable by neural networks, now we have found a unique class of approximators, the neural networks, that are all optimal for every function class, independently on the use, independently on the nature, independently of what they're modeling. And this is why this framework is so powerful, because we went from having a lot of different dictionaries from every single function class to having just one universal approximator that approximates every single function class. And now, there is to be said like still something about the fact that like I'm talking like if all those dictionaries are actually effectively representable by neural network. Actually, they are. So one have to check that, but like that's not hard. This you can because these dictionaries are very well characterized, so you can write them in very like explicit form. So you can just build essentially neural networks that approximate them properly, and then you have that all function classes are actually optimally representable by neural network. And I think this is very cool because one thing that was like for a long time, studied and like tried to be understood, and then people also have come up with very beautiful idea on those things. Now is everything unified just after neural networks, and so the idea behind all this theory is also that neural networks work so well in the tasks that the people try to use them, because essentially we are always trying to learn functions from here, and you don't even need to really understand where you are. You just use a neural network because it's going to be efficient, because because it is, and so it's going to learn fastly the right object to approximate your function from your original function class. Because previously, if you were using AlphaCarvlet to approximate some other class, then like you would have been stuck because they were not the right object. But now you have like a universal object that is just approximating everything. And so that's also why, then the idea is that this is also why neural networks work so well in the practical task in which they are used. Now, as I said, one could also say a lot more than just this for also other deep learning objects that have been used. And in particular, again, also the idea, so you can also try to explain the success of recurrent neural network, of transformer, of a lot of different objects, with essentially the same ideas that we just used here. So by employing this Kolmogorov-Donoho rate-distortion theory and using a lot of other results that in the past have already been showed, and try to translate the result to the field of like neural network approximation or recurrent neural network approximation or transformer approximation or whatever you want. So this is just what I want to say about like what one can say also for other different objects. And nothing. This is it. This is what I wanted to present you. And thanks for listening. And thank you. If someone a question, you can ask question. Otherwise, we can. I think we can go. I don't know what we can do. Okay. Okay. Can you? No. Can you make the question short? I don't know. No, wait. You're saying we are controlling the depth actually, but the depth actually goes to infinity. Yeah? When m goes to infinity, the depth also. Yes, because it's just like polylogarithmically bounded, but like the logarithm goes to infinity, and then the polynomial of the logarithm also goes to infinity.
Was there also a constraint on the depth? There were so many.
Like the constraint on the depth is more equal than pi log m. So as m goes to infinity, this goes like the length you're allowing is also going to infinity. Yes. It's like for fixed m, it's fixed. So for fixed m, it's fixed. But actually also, I also lied a bit, because actually it's also fixed the length, like also when you just put the constraint on the connectivity, because like the connectivity is the number of nodes that are like essentially that you can active, and you cannot most active, like you can do, like there is a bound on the depth that you can have, but you want to have like a stronger bound essentially.
Is there a specific reason why you choose L2 space instead of like the L2 norm instead of any other one? Would that affect the optimal dictionary or a specific sense?
I think that the main reason why you work in L2 spaces is that always because like every signal in signal processing is always assumed to be essentially of finite energy. Essentially, that's the reason why. So you most of the time choose to have it like to have it like you want to have like a norm that is finite. You want to be able to work with those elements. Now, if you change the norms, I think For certain kind of norm, I think you can actually change the norm. Maybe if you use like LP norm or something. I don't know, I'm just guessing. I think for LP norm, you can adapt those things. I'm not sure if you can adapt this for like L infinity norm or for things like those. That I don't know. But I think the main idea for using for picking those for those function classes in L2 is that like at the end, like they're always like in application, they're always like you're always making that assumption the energy of the signal is finite.
Thanks for the talk. For me, it's really a curiosity. At the beginning, we assumed that like the neural network is a ReLU neural network, and if you change the activation function, do you have other bound that are in some sense like more tight, and you can shrink a little bit
I think.
polynomial, or this is a huge.
No. I think that's a very good question because like all this works with ReLU neural networks as you observed, but I actually think that like these kind of like heavily rely on the fact that like this whole theory like rely quite heavily on the fact that like it's the ReLU neural network. So I don't know like if I think like they haven't tried because at the end also like all those results are very cool results but are also very theoretical results. So maybe you say okay. We already have one result. Okay, maybe it makes sense also to go for the other activation function. I think for certain activation function, it also works. You can also adapt it. And in general, the idea is that you can always use those frameworks to do whatever you want for like any kind of like activation function whatsoever. But like I don't think there are like other results for or at least to my knowledge, there are not other results for different activation function. And also like the reason why they chose activation function is that also like this is also like a very common like choice for like just like applications. Okay, I think questions are over. Thank you for being here and nothing. I think the pizza is arrived, right? Okay, cool. Okay, thank you.